and welcome to this video on alcohols. This is for the AQA specification. My name is Chris Harris and I'm from AlleryTutors.com, and this video is a revision video. So that means we're just going to do a quick overview of the alcohols topic, the whole topic for AQA. The PowerPoints that I'm using here can be purchased. So if you want to use them for your revision in addition to your books and notes, etc., then you can. If you just click on the link in the description box below this video, and you can get them from there. Like I say, all these videos are linked to the specification, and here are the specification points for the AQA syllabus. Okay, so let's make a start. So this is going to look at the introduction to alcohols, so find out what they are and just learn a little bit about them. So alcohols have the functional group OH, which is called the hydroxyl. That's basically the homologous series. All alcohols have an OH group. Okay, so we've got different types of alcohols. The first one could be a primary alcohol. So primary alcohols have just one alkyl group attached to a carbon, which is obviously attached to the OH. So this is an example, butanol. That's an example of a primary alcohol. Secondaries have two alkyl groups attached to the carbon with the OH on. An example is butan-2-ol, and there's the structural formula. Make sure you're able to obviously read structural formula and see how it links with the displayed formula, which is this one up here. Okay. And tertiary alcohols, these have three alkyl groups attached to a carbon with the OH on. So for example, 2-methyl-propan-2-ol is an example of a tertiary alcohol. Okay, again, there's the structural formula. So make sure you know about your primary, secondary and tertiary alcohols. These are going to be important because they react differently when we oxidize them. Okay, so let's have a look at dehydration of alcohols. So alkenes can be made sustainably from alcohols, providing the alcohol has been made via fermentation of glucose from plants. So this is used quite a lot to make things like plastics from plant material, etc. This is quite useful. So what we do is we just eliminate the water from the alcohol, and from that we make our alkene. And the reaction of removing water from a molecule is called dehydration, which sounds pretty obvious really, because you're removing water. And using it, we can use the alcohol made via fermentation, which we'll look at in a minute, and we can use that to make your alkenes. It's much more sustainable doing it this way because you can regrow. It's a renewable source because it's plant material. But your alternative is using crude oil, but this is non-renewable. So using crude oil to get your alkenes isn't the best method. Sometimes we have to do that though, but if we can avoid it, then that'll be better. So alkenes are mainly used to make polymers. So for example, plastics. That's pretty useful. And this reaction involves the use of an acid catalyst. So either we're using sulfuric acid or we're using phosphoric acid, which is H3PO4. Sulfuric is H2SO4. So here's the reaction. Look, there's your alcohol. We remove water from it. There's the water, and we form ethene. Okay, so this is the example of dehydration of alcohols, again using a more sustainable method. Okay, elimination reactions. So dehydration of alcohols can be illustrated using an elimination mechanism. Okay, so again, more mechanisms here. Make sure you know how to do them. Okay, so there's our alcohol. And the first thing that happens is we've got that lone pair. We've actually got two lone pairs on the oxygen, but we've just drawn one on here. So we've got a lone pair on the oxygen on the alcohol. What this will do is this will attach to the H+ ion, which is basically come from an acid catalyst. So the ones that we mentioned before, sulfuric acid or phosphoric acid. Then what we do is we form this intermediate, and you can see this oxygen intermediate. The hydrogen's added onto this oxygen, but now the oxygen has got too many bonds. It can only bond twice, remember, but it's got 3 bonds. So we have this positive charge in the oxygen. And what happens to stabilize this oxygen here, the electrons in this bond here jump into the oxygen. This is your kind of intermediate, this bit here. So this is going to jump into the oxygen, and we're going to stabilize this oxygen atom here. And we have this carbocation intermediate, this bit here. So this is what we're talking about here. So we're leaving this carbocation intermediate. Basically what happens is this is obviously not very stable because we've got this positive charge here, and neither is this, to be honest. So what happens is the electrons in the CH bond here, the one neighbouring the one with the alcohol on, that did have the alcohol on, breaks, and the electrons from this bond go into here to try and stabilise this carbocation, and we form a CC double bond. Notice we've lost water as well, because water was attached, it isn't now. Okay, and you can see here we've got ethene. There's our ethene there. The H plus is reformed, and also we have water as well. Okay, so this is proof that this is a catalyst because it was used here and it's remade back again here. Water has been eliminated as a dehydration reaction, and obviously we have ethene as well. That's our alkene. So make sure you know this mechanism. It's really important. Can be a bit fiddly because you've got two positively charged intermediates here. In the middle. Make sure you know what's going on. So there's a lot of like internal rearrangement here. Okay, right. So let's have a look at the dehydration of non-primary alcohols. So that one was fine because that one was a primary alcohol. But if you've got a non-primary alcohol, you can get two different alkenes. Okay, so the double bond can be formed either side of the carbon that did have the hydroxyl group on. So here's an example here. This is a secondary alcohol. You can see we've got two carbons either side of it there, and there's the alcohol in the middle. So what happens if I add sulfuric acid to this reaction, I can either get my double bond forming there, okay, which is this product here, or I can get my double bond forming there, which is this one here. So obviously you can see that we get two different products. You need to be aware of that, and that happens obviously with secondary, with non-primary alcohols. So if you get a secondary one like this, then you know what you're looking for. Okay, so as long as you're kind of aware of that. Okay, distillation. So dehydration of alcohols is conducted via distillation. Okay, so when we undergo the dehydration of an alkene, we get an impure product. Okay, so we get some impurities in there. And this impure product contains alkene, alcohol, water, and acid. So we've got loads of different things here. So what we need to do is we need to separate the useful alkene, the bit that we want, from all the impurities that we've got. And basically distillation is a method in which we can do that. And basically it works by separating the components out according to their boiling points. So this is a distillation kit here, as you can see. So you've got your impure product here, you've got your thermometer, you're basically heating it up gently. This is an iso mantle or electric heating element, and this is your Liebig condenser going down here. Okay, and we're collecting our products at the end there. So distillation, obviously we could separate it out, but even though, despite us doing that, we still need some further separation because we might still have some impurities remaining in here. So what we need to do is we need to use a separation funnel, and what this can do is this can help. This basically can help separate your products. If you add a drying agent in there, then this can be used obviously in here. This could be used to remove any water that may be still left in your sample in your alkene. Remember, you just want pure alkene. You want to try and get rid of that water that might exist in there. Okay, so yeah, using this will separate your aqueous layers and your organic layers using a separating funnel. Okay, you need to know this very specific reaction, okay, for AQA. So this is making cyclohexene, okay? There's a lot of steps here. Now, obviously, you need to know these practical techniques and why we do them and what we use. There's quite a bit of detail in this one, and very practical based, this one. So the first step we have to do when we're making cyclohexene is we're going to use distillation, okay? So we're making cyclohexene, we're making that from cyclohexanol, so this is a type of alcohol. We're going to use distillation, separation, and purification techniques. There's a lot of things here. Right, so listen very carefully. Right, so first one, distillation. Okay, so what we do, like we've seen in the previous one, is we add our concentrated sulfuric or phosphoric acid, any of them, and cyclohexanol into a round bottom flask. There it is there. We're going to add a few anti-bumping granules as well, and basically this is going to allow a smooth boiling process. You might have seen it if you've ever tried to cook soup in a pan or in the microwave. When you heat the liquid effectively knocks into each other, and it ends up splattering all over the place in the microwave. Now, one way where you can get around that is by stirring it, because by stirring it, you're helping to distribute the heat around. Now, all these anti-bumping granules do this. Obviously, we can't just keep stirring this. And what we've got to do is try and absorb some of the energy that might be in some of these particles here when we heat it. And the anti-bumping granules just absorb some of that and stop it from becoming violently, like boiling violently and causing damage. Okay, so that's all it is. Right, so we're using a heating mantle, like we said before, and we're going to warm it to about 83 degrees Celsius. This is the boiling point of cyclohexanol. Okay, so we're just going to boil that. And we don't use a Bunsen burner. That's really important. We're using an electrical heating element here. This is plugged in because cyclohexanol is flammable. If you put a Bunsen burner under there and you get vapors of cyclohexanol coming off, you've got a fire in your hands. So it's an important safety point. Okay, so the chemicals with a boiling point less than 83 degrees Celsius, these will evaporate. So these will come off and these will drive off into the condenser. And they will basically cool down when they hit the condenser and run into this container here. Okay, so the condenser, remember, has cold running water running through it. So you've got an outer wall here with water running through, and that basically cools the liquid, the vapor, as it comes down here into a liquid and runs down into the container. Now, this is a measuring cylinder, but you can use a beaker. It doesn't really matter. So this is obviously collected, your product. This product will have small amounts of impurities in those. So you've got some unreacted cyclohexanol, and you've got water in there as well. So you'll have some other things in there that we need to try and remove. But on the whole, we have some of our product in there, but we need to get rid of these impurities. So that's the first step, is distillation. Okay, so the next steps, so steps 2 and 3, is basically separating, or called separation and purification. So, and we need to know, obviously, the difference between them. So let's have a look at step 2, separation. So we've made our product, we take our product from the distillation, and we start to separate it. Basically, what we're doing is we're going to add water, and the water is going to dissolve some of the soluble impurities that are still around. Okay, so adding this in here, some of the soluble impurities will dissolve in here, and we're left with our valuable product, the bit that we want, which is cyclohexene. We want that separately. Okay, so let's have a look. So after allowing the solution to settle, we get 2 layers, like I say. So we get the cyclohexene layer. This is the top layer. This is impure. Remember, we've still got some impurities in here, but any of the soluble impurities will be dissolved in the water that we've added to it, and these will just be dissolved in this layer and the bottom here. And all we want to do is we need to drain the bottom layer off, remove this bit, and keep the alkene layer. You've got to remember to take that stopper off as well, because obviously if you need pressure to push this down so we can get this here. If you keep the stopper on, then you'll find it won't run out. And the last step, really, well, step 3 is to purify it. So once we've got our product in there, we're going to take this impure cyclohexene, okay, from step 2. So that should say cyclohexene, not ane. Okay, from step 2, and add it to the round-bottomed flask. Okay, so then what we do, once we've added to the round-bottomed flask, we then add a drying agent. This is what I was talking about before. Anhydrous, so that just means without water, calcium chloride. And basically this will remove any aqueous substances still remaining. And then what we do is you invert the flask and we leave it for 20 to 30 minutes. And what you'll find is some clumping, basically. So this powder is really dry. You add it in. When it starts clumping together, it means it's absorbing water. And we can keep on adding it until it doesn't clump together and we've got freely moving grains of calcium chloride. And that means all the water has been removed from your sample. So it's a great way of trying to remove water from your sample without actually heating it. Okay, so let's have a look at the hydration of alkenes. Okay, so we looked at this a little bit in the alkenes topic as well, but it's just another way, a bit of information because it fits in with the alcohols topic. So we basically produce these by the hydration of alkenes. So this is adding water. Instead of dehydration, which is removing water, this is adding it. So we're going to use steam and an acid catalyst to create an alcohol. We can obviously react the steam and ethene together with a phosphoric acid catalyst. 300 degrees Celsius, 60 atmospheres of pressure is needed. So anything like that will be fine. Right, so there is your alkene. There's your acid. Okay, what happens is the electrons in a double bond, they're used to form a bond with a H+ ion. So there it goes. Okay, so these are your mechanisms here. So make sure you be able to obviously write these down properly. We get this carbocation intermediate, look. Remember the hydrogen's being added on, it's added on here. Lone pair on the water, remember this is hydration, or the steam, this comes from the steam, basically bonds onto the carbocation. There it is. Okay, so lone pair onto the carbocation. And then we produce this product here. Now you can see, because we've added the whole water molecule on, water's now got 3 bonds. It shouldn't have 3 bonds, it should only have 2. So you've got this, obviously, O plus here. Okay, so you've got this positive charge here, this cation. And so what we have to do is try and stabilize this, and the electrons from this bond here jump into the oxygen to neutralize, or to, well, neutralize, to kind of stabilize this oxygen and turn it into normal oxygen. But this hydrogen is lost, okay, because we've broken this bond, the hydrogen falls off. There it is, and there's your product. Okay, so we've got the product here, which is your CH3, CH2OH, so that's your alcohol. This is ethanol, and notice your H plus ion has also been removed as well. So there's the H plus, and this is your acid. Your acid has been reformed, and that's proof that it's a catalyst. So we had the H plus at the start, and we've got the H plus reformed back at the end, and we formed our alcohol. So as long as you know this mechanism, that's the main thing. Okay, so let's look at fermentation. Remember we looked at that last time as a sustainable way of producing an alcohol, or alkenes, because you make alkenes obviously from alcohols. So it's basically just an alternative to ethene and steam when making ethanol. So fermentation, unlike the previous step where the ethene was taken from crude oil, this is just a different way of making your alcohol. So this is, like I say, it's a more renewable source, and it's basically used from glucose from plants. Okay, so fermentation uses yeast in anaerobic conditions. That means no or very little oxygen. The reaction is really exothermic, well, a little bit exothermic, so you get a little bit of heat produced as well. So there's the reaction, look. There's glucose, C6H12O6. The biologists amongst you may recognize this very well. You also produce ethanol. There's your ethanol there, and you produce carbon dioxide. So this is a fermentation process. Okay, so glucose will produce ethanol and carbon dioxide. Okay, and the yeast is an enzyme. It converts this glucose into carbon dioxide and ethanol. It has to be at the right temperature though, because it's an enzyme. You can't just heat them up like in the previous reaction that we've seen before. You have to heat it at the right temperature, because enzymes prefer to work at certain conditions. So let's have a look at the effect of this. So you can see here, this is the rate of reaction. This is the rate at which we're converting glucose into ethanol. This is the temperature on the bottom here. Now, this enzyme prefers to work between 30 and 40 degrees, and the vast majority of enzymes do. So we've got 30 to 40 degrees Celsius. This is the optimum temperature for the enzyme to work. So when we're doing this reaction, we need to keep it at around this temperature here to actually make sure that we are getting the most out of the reaction, so to speak. Okay, so this is the fastest rate of reaction, and we need to try and get the most product. Okay, the reaction's too slow at lower temperatures. So at lower temperatures, it's not quick enough. Really, in industry, you need to make it as quickly as you can, because time is money, as they say. And at this side, the enzyme's denatured. That means it's the active site, the shape has permanently changed, and therefore it won't work. And you can't get the enzyme back again once you've denatured it. So at high temperatures, you can see it drops off very quickly. We can't heat it too high. Okay, fractional distillation is then used to obtain your pure product. So once you've got your alcohol, you then distill it, and you just purify it, and you make sure you get as much alcohol as you can. The great thing with fermentation is it requires not much, very little equipment at all. It's a really cheap process, and the cost as well. I suppose the biggest cost for this is the fractional distillation, but that obviously that requires a bit of heat, and you'd have to pay for the energy for that, etc. But overall, it's a cheaper process. The problem is though, it's quite slow. You don't get a massive yield from this as well, but nonetheless, it is more renewable than for crude oil. Okay, let's look at biofuels. Now, biofuels such as ethanol is made from dead biological matter. Okay, so we need to know about all these. So ethanol is being used as a fuel, and it's good in things like in countries like Brazil because they produce lots of sugarcane. Sugarcane obviously is a good supply of glucose, which then can be converted into alcohol, which can then be used as a fuel. So Brazil is one of the biggest users of biofuels in the world, and basically they just add it to their petrol in their cars. Basically, sugar is fermented. You produce the alcohol, and here's just a picture of sugarcane that's been harvested. Okay, so the advantages of this, they're renewable, more sustainable than crude oil, and the biofuels produce carbon dioxide as well, so when they're burnt. However, it is carbon neutral. Okay, so the carbon dioxide is absorbed when the sugarcane is growing. So when we burn the fuel, yes, we put the carbon dioxide up into the atmosphere, but the crop absorbs the carbon dioxide from the atmosphere, so we class it as carbon neutral. Well, nearly, just about. Okay, disadvantages though. So it is expensive. Like I say, converting petrol engines to take fuels with higher levels of ethanol, you have to convert them engines. That can be quite costly. And obviously this land here, all of this land has been used for fuel. Now this land could be used to grow food on, and especially in some countries where food is in short supply, some people just disagree with the idea that we should be using land purely to fuel cars. And obviously this is quite an expensive way of using land just for fuel. So yeah, that's the downside. This is taking up land which could be used for food. When I said about the carbon neutral bit, like I say, it's nearly carbon neutral, and you need to know the reasons why. Okay, so when we burn this ethanol, a greenhouse gas, carbon dioxide, is produced when we burn it, so that's not particularly good. But this is used by growing plants in photosynthesis. Okay, so you might think, well, surely that is carbon neutral. So if we have a look, let's break it down. Okay, let's have a look. So you can see here that plants take in 6 moles of CO2. There's the equation. Okay, so this is just photosynthesis. Okay, they produce the glucose that we need. Okay, so during the fermentation process, though, ethanol is produces 2 moles of carbon dioxide. So when we ferment this, we produce carbon dioxide. This goes up into the atmosphere. So producing 2 moles of carbon dioxide, and there's our ethanol. When we burn the fuels, we take the ethanol and we burn it, we produce 4 moles of carbon dioxide. So you can see here that 4 moles of carbon dioxide have been produced. Now, if you look on there, the total number of moles of carbon dioxide used up is 6 moles. There it is there. Okay, and the same amount of moles is produced, 6. So 2 and 4 is 6. So you might think it's carbon neutral. However, like I say, it's not completely carbon neutral because we're using fossil fuels to transport the biofuel across the country. These fossil fuels haven't been used from this process here. Remember, we still use crude oil to make the fuels. Biofuels are mainly mixed with the alkenes that's dug from the ground in crude oil. So and also fossil fuels are used to make the fertilizers. And obviously the fertilizers help this crop to grow, so you've got to be careful of that. The machinery used to harvest the crop, if you're using combine harvesters, they're going to put carbon dioxide in the atmosphere. So it's nearly carbon neutral, but not quite. So as long as you know these little exceptions as well. Okay, let's look at the oxidation of alcohols. So these can be oxidized to aldehydes, ketones, and carboxylic acids. Okay, and we use potassium dichromate as our chemical. And what this is a mild oxidizing agent, and it's reduced itself. And what you're looking for when you oxidize these things is dichromate is like an orangey color. It's like a pale orange color, and it'll turn green. Okay, so when you've oxidized something using dichromate, you'll see this color change, orange to green. And the green is the chromium ion, which is Cr3+. Okay, so your primary alcohols, these can be oxidized to aldehydes and then to carboxylic acid. So there's your aldehyde there. This is aldehyde, ends in al, remember? It has a C double bond O and a CH on the end carbon. There it is there. Okay, so this is an aldehyde. But it can be oxidized further to a carboxylic acid. These end in oic acid. Now, if you look at, they're very, very similar, except this has now got an OH on here, and we've got a C double bond O there. So this is basically a carboxylic acid. Secondary alcohols, these can be oxidized to ketones. So there's a ketone there. So ketones are very similar to an aldehyde, except the carbonyl group, this bit here, the pseudo bond O, is now sitting in the middle carbon instead of on the end. So very, very similar, but this is called a ketone, and we end it in -one, so like butanone, etc. And tertiary alcohols, they can't be oxidized using dichromate because it's only a mild oxidizing agent. You can burn them though, obviously, and you can oxidize them that way, but that isn't really much use because we don't get any useful products from it. We just get carbon dioxide and water. Okay, so let's just look at them in a little bit more detail. Okay, so we use distillation and reflux is used when we're oxidizing alcohols. So primary alcohols are oxidized, but the products produced are dependent on the method followed. Okay, and it's really important that you know the methods and the types of products that we get. We're going to represent the oxidizing agent as just O and a square bracket because it makes it a lot more easier to kind of read. Okay, so here's our primary alcohol. If we oxidize it, we can get an aldehyde. Okay, now the problem is that if we oxidize it strongly, we also get a carboxylic acid. Okay, and it's difficult to just extract the aldehyde when we're just heating in a boiling tube. So we need an alternative method. Okay, so what we need to do, as soon as we form the aldehyde, we need a method by which we can remove it straight away so it doesn't react further to a carboxylic acid. And we use distillation. Okay, so distillation is used here. Aldehyde is a lower boiling point in the alcohol, so as soon as it vaporizes, we collect it and use it for what we need to do. Okay, if we oxidize further though, if we use reflux, here that's a reflux setup. So you've got your round bottom flask and your heat source. Your Liebig condenser is now vertically upwards, water in, water out. Reflux, an excess oxidizing agent. Then what we do is we make a carboxylic acid. So here we're using 2 lots of oxidizing agents compared to 1 molecule of alcohol. So this is called an excess. And we produce our carboxylic acid. Okay, and the reflux basically allows us to heat this alcohol strongly with the oxidizing agent, and the chemicals evaporate. They start to evaporate. They hit the cool condenser, and they run back down into the condenser and re-react. And they keep doing this all the time, up and down, up and down. And basically, you don't lose any product out the top because it cools against this cooling water that's running through the condenser. So refluxes are really useful for heating volatile chemicals or reacting volatile substances which evaporate easily. Okay, secondary alcohols, these are oxidized to ketones, and it's difficult to oxidize ketones further, so basically we can just use a reflux setup, and we use an oxidizing agent. Again, we're going to use this letter O. Okay, so here it is here. So here's your secondary alcohol. We're going to use reflux and an oxidizing agent, and basically we're just going to make a ketone. So this is dead easy, really. There it is. So your secondary alcohol will, like propan-2-ol, for example, oxidize to propanone, which is your ketone, when the acidified dichromate is added. And you'll see this color change of orange to green. Okay, so the dichromate has been reduced, the alcohol has been oxidized. 1 load of oxidizing agent is required, and there's the reflux setup just as a reminder. Okay, so finally we just need to know how we can test for these things. Obviously we produce them, but they all look pretty much the same. They're all colorless liquids, so we can add do what we'll call wet lab testing, and we can add either Fehling's or Tollens reagent. These can be used to distinguish between these aldehydes and ketones. So both Tollens and Fehling's are actually, or sometimes it's known as Benedict's, a slightly different makeup, but they're pretty much the same. They're both oxidizing agents, so they will actually oxidize your alcohol or your aldehyde. So what they do is they oxidize the aldehyde, but they won't do it with ketones, okay? Because ketones really difficult to oxidize ketones further, but aldehydes can. So we can use this and we can get a visible change. So let's have a look at Fehling's. So Fehling's solution is a blue copper-based solution. You might have made it up into 2 parts. You might have had 2 parts and mixed them and activated them. Basically, you add warm aldehydes Okay, it must be warm, otherwise the reaction doesn't really work. It takes a long time to work. So you just put it in a water bath and warm it up. And Fehling solution goes from a blue solution to a brick red precipitate. You must include the word precipitate. Okay, this brick red precipitate is copper oxide. Okay, now it will do that if you've got an aldehyde present, because aldehydes can be oxidized. Ketones can't be oxidized though, so the solution remains blue. So that's a way in which you can distinguish between them. And the other test is Tollens. Tollens is a nice one because you get this silver mirror being formed. And Tollens reagent is this silver with two ammonia molecules bonded to it. We call this a complex. It has a positive charge. And again, it's added to warm aldehydes and ketones. So with the aldehydes, Tollens is reduced. This is your Tollens reagent. It's reduced to silver. Okay, this coats the inside of the flask and you get this lovely silver mirror effect. And your ketones, because they can't be oxidized, you get no silver precipitate forms. So basically, both of them show positive tests. You get a positive change. With aldehydes and ketones, you get nothing. So basically, that's just a way in which you can identify or distinguish between these two. Okay, so make sure you know them too. It's pretty important. And that's it. That is the whole topic for alcohols. It's quite a difficult one. That there's a lot of practical technique in there, and you've really got to be switched on and explain all the practical techniques. And obviously, the oxidation of alcohols, etc., is very important, and also the green aspect again comes through. So so a pretty comprehensive summary of the alcohols topic. But again, these PowerPoints, they're available to purchase if you would like to get a hold of them to supplement your revision. Then if you just click on the link in the description box below this video and you can get them there. But that's it. Bye bye.